We're in, we're in section 5.3. It's about independence. So you may know about independence, like you're independently wealthy, or you're independent of your parents, or things like that. You're acting independent of the law, pick a thing. But independence here is a concept that's in probability. It's something like those concepts, but not exactly. So here's what it looks like. It says events A and B are called statistically independent if the probability of A and B, so that's A and B both happening, is the probability of A happening times the probability of B happening. So this will hold if knowing A or B has happened does not alter the probability of the other happening. So you might say, well, pick a thing, right? So maybe you're playing the lottery. You buy a ticket today, and you find out I didn't win. Your chance of winning tomorrow, if that's your other thing you're worried about, hasn't changed. So winning today or winning tomorrow would be events that are statistically independent. On the other hand, if you were, say, buying up tickets, if you could do this, buying up raffle tickets. So there's 200 raffle tickets. And you buy a raffle ticket, and then your friend says that ticket didn't win because they're running the raffle. Then the chance that you win on the next, if you buy another ticket the next day, has gone up because you've eliminated one of the ways you could lose, and now you have fewer tickets, and the winner's still in there, and the chance of winning on the second go is now bigger because you didn't win on the first go. So those aren't independent. And you know, in things like that, even in lotteries, sometimes people who have a lot of money discover, based on the size of the pot, if they just buy most of the tickets, they're going to win and they'll make money. So that kind of thing can happen even in lotteries. Not in the one run by our state, though. You can buy as many tickets as you like. The more tickets you buy, you have the same chance of winning the next time. So ticket buying in most lotteries, one ticket's winning chances are independent of another ticket's winning chances. Here we go, though. So here's an example. Roll a die, then toss a coin. We want to verify this formula. Why does this formula work? So here's how it looks in a situation where you know the two things don't have anything to do with each other. So rolling a die, you're tossing a coin. Seeing the die face that shows or seeing the coin, one shouldn't influence the other. Once you see you rolled a 6, the chance of getting ahead should stay a half. I see no reason for it not to. And so that would say these two events should be independent. And then we'll see how independence forces this product to happen. So here's A is the die is the 6, B tosses the head. Okay. And you think about repeating the experiment. Now the experiment involves these two things. So you do both of these many times. In many repetitions, in about 1/6 of the rolls, or in 1/6 of the repetitions, you get a 6. The chance of getting a 6 is 1/6. So in many repetitions, you're repeating both of these things. In about many repetitions, the die is going to come out 1/6 of the time to be a 6. And then, in about half of those, this should be a 1/2 here. That scared me. Then, you look at those to where the 6 happened, and half those should be heads. Because just because you pick the outcomes where you get a 6, which happens about 1/6 of the time, of those, about half of them should give you heads. So that says overall, to get the number of times you get a heads and a 6, or a 6, it's a 6 and a heads. So first you have to get a 6, and then you have to get a heads. So 1/6 of the time, and half of those. So half of those, and then half of those means you take the 1/6 times the 1/2. 1/6 times 1/2 gives you 1/12. About 1/12 of experiments, the roll is a 6 and the toss is heads. So that means the probability of A and B is 1/12. So you notice how that looks, since it's the 1/6 times the 1/2 is the 1/12. That's this formula. Probability of A and B is probability A times probability of B. And so we're thinking in any old situation, if you've got two events, the chance you see an outcome in the first event is probability of A. So in about that fraction of experiments where you're combining two things together, A happens, and if A and B are independent, then among those, the fraction of the time that B happens is the same fraction as if B was observed by itself. And so you get probability A and B equal probability A times probability of B. Now this seems pretty straightforward on first glance, but it was a struggle for the people who invented probability to figure out exactly how to handle independence, even understand how to do it. This seems like a pretty simple formula that describes a pretty complicated thing, saying that observing one type of event occurring hasn't changed the probability of the other one occurring, and all we're doing is multiplying some probabilities together. Seems like a simple-minded way to verify something that's actually sort of complicated, but it does work. So because of that, we can check for independence just by verifying the equation. We don't have to do anything else, which is kind of cool. So here's my example. Here's events. So I'm come to work every day. I come on the highway, and sometimes I'm late for work, but not too often. And sometimes late, probably more likely to be late going home because I run out of time during the day. So here's the thinking. Probability that A happens for me is maybe 10% or 0.1. That's 1 in 10 days I'm late making it to work. Of course, that doesn't mean I'm late for class. I'm just late for my usual time I show up. And the probability of B, late returning on a random day, is 0.2. About 1 in 5 days, I don't get home at the regular time. I get home a bit later. But then if I was to track both of them at the same time, I think the chance is 0.05. About 1 in 20 times is both. That's my experience. And you're wondering if being late for work influences whether you're late going home. You figure if you're late for work, maybe you have to work longer, and that'll make you more likely to be late going home. So that's the idea, but here we go. Let's see if it is. So here's how we do it. We look at this equation, we put these quantities in. So we say, is the probability of A and B equal to the probability A times probability B, or is 0.05 equal to 0.1 times 0.2? No, because the answer to that is 0.02, not 0.05. So to be independent, we need the probability for A and B to be independent. We would need the probability A and B to be 0.02, but in fact it's 0.05. That says this product is too small. Too small. What's it? Wait a minute. No, this product. Sorry, both of the things happen together with probability 0.05. It should be 0.02 if they're independent. So this probability of them both happening is slightly larger than you would predict. Here's independence says it's 0.02. Here's reality says it's 0.05. So it's a little bit larger than independence would show, and that says you're a little more likely to be late. You're a little more likely for both of these things to happen together than if they were behaving independently. So maybe being late for work causes you to be late going home a little more frequently, and then when you're not late for work, you're not late going home a little more frequently. So these probabilities balance out. So we check the product. We see it's not. We see it's not the actual probability. We see the product is too small. This is too big. So these two things happen together more frequently than you would predict using independence. Okay, we made it through the first slide, and we're moving on with independence.